This lecture is going to be on Kepler's three laws of planetary motion. A little history lesson tells us that the 16th century, the nature of the orbits of the planets was debated along with geocentric and heliocentric models of the solar system, where people actually thought that the geocentric model was correct, where the Earth was the center of the solar system, even the universe, and that later changed or evolved as the science got better into the heliocentric model to where the sun is the center of our solar system. Johannes Kepler was a German mathematician who initially sought to prove that the planets orbited the sun and that their orbits were perfect circles. In order to prove this hypothesis that the orbits of the planets were perfect circles, Kepler used data collected by Tycho Brahe, a Danish astronomer who at the time had made the most accurate measurements of planetary movements available. But like two pieces of different parts of a puzzle, Brahe's and Kepler's hypotheses did not fit together. Rather than giving up and manipulating the data, Kepler rejected his original hypothesis and, like the true scientist he was, analyzed the data before him. So let's take a look at what he discovered. First, Kepler discovered the planets orbit the sun in ellipses rather than perfect circles. An ellipse is a shape that results when you attach the ends of a piece of string to a piece of paper. Stretch the string tight with the tip of a pencil and then draw around those points while keeping the string taut. Each of the points at the string of which the string is attached is called the focus of the ellipse. The closer the two foci are together, the more nearly circular the ellipse is. In fact, the circle is an ellipse where the foci is in the same place. As the two foci move further apart, the ellipse becomes more and more elongated. The amount of elongation is called eccentricity. Circles have a zero eccentricity value. Here you can see the foci are spread apart, has a greater elliptical value, is more eccentric. Here's less eccentric, and this would be zero eccentricity or perfectly circular. Kepler found that the orbit of each of the planets, or orbits, were an ellipse with the sun located at one focus. This is now known as Kepler's first law of planetary motion. Kepler also discovered that eccentricity of the planets and other objects is not the same. For example, the Earth's orbit is nearly circular. Mars has the most eccentric orbit of any planet, and Halley's Comet has a very extremely eccentric orbit. The next discovery that Kepler made while analyzing the planetary data had to do with the speed at which planets move. Kepler discovered that the planets move fastest when they're closest to the sun and slowest when they're furthest from the sun. This is Kepler's second law, which is also referred to Kepler's law of equal areas. It states that the imaginary line connecting the planet to the sun sweeps out in equal areas in equal time, regardless of where the planet is in its orbit. Here we can view areas A, B, and C are equal. Consider them like pie pieces. They're all the same amount of pie or pizza. Note that this law applies to only one object at a time. The area swept out in the Earth in a given time is always the same. Likewise, the area swept out by Halley's Comet in a given time is the same. But the area swept out by the Earth and Halley's Comet are not the same. So we can only compare one object at a time. We can only look at the orbital sweep one at a time. Kepler's first law describes the shape of the planetary orbits, but his second law describes how the speed changes as it makes its orbit. But neither of these laws tell how long it takes a planet to complete one orbit of the sun, nor do they tell us the time depends on the distance between the sun and the planet. Planets that are close to the sun do not have as far to go to complete one orbit, so the further they are, it takes longer. Kepler discovered the more distant planet is from the sun, the larger the circumference of the orbit, and the slower the speed of the planet. Kepler's third law states that the square of the period of the planet's orbit measured in years is equal to the cube of the semi-axis major of the planet's orbit, measured in AUs, or astronomical units. Remember, 1 AU is the average distance between the sun and Earth. So here's how Kepler's law plays out, Kepler's third law. The relationship was so beautiful to Kepler that he referred to it as harmonic law, or more poetically, the harmony of the worlds. Kepler is honored today not only for his discovery of the three laws that describe all celestial bodies, but also for his commitment to understanding the true nature of the universe, even at the expense of his cherished hypothesis. Johannes Kepler can be described as one of the first true scientists. First law, law of ellipses. Second law, law of equal areas. And third law, the law of harmonies, where p squared in years equals the distance in AUs cubed. And there you have it.